Could a quantum computer actually be the secret weapon for predicting who's going to default on their credit card? I know, it sounds a little like science fiction, right? But a team of researchers decided to put that exact question to the test. We're going to break down how they used a 256-qubit quantum machine to tackle a very real and very expensive financial problem.
So here's our game plan. We'll start with the huge challenge banks are up against. Then we'll get into the quantum solution they tried out, walk through their cool hybrid strategy, and meet the villain of our story, which is hardware noise. And then finally, we'll figure out what this all really means for the future.
All right, so let's set the stage with the problem itself. It's basically a high-stakes guessing game that banks and financial companies have to play every single day.
I mean, think about it. It's a question that impacts millions of us and, billions of dollars. How on earth do they figure out if someone is likely to miss a payment next month?
Well, the answer is it's an absolutely massive data puzzle. Banks have to sift through just mountains of information: credit limits, age, marital status, payment history, you name it. And they're searching for these tiny, almost invisible patterns that might signal trouble ahead. Even for our most powerful classical computers, this is a really, really tough job. So, to give this a real-world test, the researchers grabbed a public data set from Taiwan. The mission was pretty straightforward: look at a client's data and predict if they'll default next month. But, and this is a big but, the data is what we call imbalanced. See, most people pay their bills on time, so trying to find the few who won't is a classic needle in a haystack problem.
Okay, so we've got the problem. Now let's bring in the hero of the story, the new tool that researchers brought into the fight, the quantum reservoir.
So what in the world is reservoir computing? Well, imagine shouting into a really complex cave. That's your reservoir. You send in a simple sound, that's your input data, and what you get back is this rich, complex echo. By just listening to that echo, you can learn things about your original shout that you couldn't hear before. It's a clever way of letting a complex system do the hard work of revealing hidden patterns for you. And here's the kicker. Quantum Reservoir Computing, or QRC, just swaps out that classical cave for a quantum system. You feed the financial data in, you let the weird and wonderful laws of quantum physics take over, and then you measure the incredibly complex echo that comes out the other side. The big idea here is that the quantum world is so complex, it might reveal patterns that are completely invisible to classical computers. And hey, this wasn't just a theory on a whiteboard. They ran this experiment on a real live machine, Queres Aquila, a 256-qubit quantum computer. You're looking at its register right here. It uses this incredibly precise arrangement of individual atoms to create that powerful quantum reservoir. Pretty cool, huh? Now, it's important to know this wasn't a quantum computers do everything kind of solution. Instead, the team came up with a really smart hybrid approach. The goal was to get the best of both worlds, classical and quantum, to get the best possible results. Their process basically had three main stages. First, a regular old classical computer takes the raw data and cleans it up. Second, that cleaned up data gets fed into the quantum reservoir. And then third, another really simple classical program looks at what came out of the quantum computer and makes that final call: default or no default. This diagram shows you the whole workflow. You can see the data flowing from left to right, it gets cleaned up classically, then goes into that quantum black box in the middle, and finally out to a classical predictor. The quantum computer is only doing the one thing it's theoretically amazing at: finding those super complex patterns. Okay, but how do you actually tell a quantum computer about someone's credit limit? You've got to translate it or encode it. The researchers tried two different ways. The first, position encoding, turns a piece of data into the physical distance between atoms. The second, detuning encoding, does it by tweaking the energy level of each individual atom. Two different languages to talk to the machine. And you can literally see the difference right here. On the left, with position encoding, the control pulse is pretty uniform. But look at the right, for detuning encoding. Each atom gets its own special little nudge. This lets the computer imprint the financial data onto the quantum system in a much more direct way. And trust me, that difference is going to be really important in a minute. All right, now we get to the real drama of the experiment. How does a perfect, flawless, theoretical quantum computer stack up against the real, messy, noisy hardware that we actually have today? And here they are, the results. This chart shows us the performance. It's measured by something called an F1 score. All you really need to know is that it's a way to measure accuracy, and a higher score is better. That dashed line you see is the score from a very powerful classical model, a deep neural network. That's our benchmark to beat. So, the first huge takeaway right out of the paper is that in a perfect world, the concept is solid. In a flawless, noiseless simulation, their quantum method did just as well as the top tier classical approach.
And you can see that right here. That blue bar, that's the perfect quantum simulation. It's right up there, neck and neck with the dashed line from the classical model. This is huge. It's the proof of concept. The fundamental idea actually works.
So, that was the ideal scenario. But what happened when they took the exact same program and ran it on the real physical Aquila machine? And there it is, the reality check. This bar shows the result from the actual hardware. You can see a pretty big drop in performance. And the culprit has a name: hardware noise. Today's quantum computers are still incredibly sensitive. They're prone to errors, and all that background noise just scrambled the signal, making it harder to spot the patterns. So, if it didn't beat the classical computer, does that mean the whole thing was a failure? Not even close. And the reason why might just be the most exciting discovery of the entire experiment. Just look at this. This table compares how long it took to train the different models. The big classical model took over 26 seconds, okay? But the quantum hybrid models? Whoa, they were unbelievably faster, in some cases taking less than 0.2 of a second. That is a massive potential advantage. The quantum part does all the heavy lifting, which means the classical part has a super simple, super fast job to do.
So let's just quickly sum up what we learned here. Number one, the basic idea works. In a perfect world, a quantum reservoir is a great tool for this. Number two, it has the potential to be way, way faster to train than current deep learning methods. Three, the big problem, the bottleneck right now, is hardware noise. And finally, number four, this hybrid approach, using quantum for the hard part and classical for the rest, looks like a really promising path forward to actually get useful results from these early machines.
So this experiment really shows that hardware noise is the big wall we need to break through. But it also gives us this amazing peek at what's waiting on the other side. So it leaves us with a really big question. As these quantum machines get bigger, better, and quieter, what other massive real-world problems are we going to be able to solve?